All right, let's go ahead and take a look at some of the information necessary to complete a selection of the questions from the test 4 material. For this first one, we're talking about a spring, something that's come up a few different times in our lessons. Hooke's law is the force on a spring is equal to the force constant of the spring, or spring constant, multiplied by the change in length. Now, sometimes the change in length is delta L, and a lot of times it's just X or Y if it's something that's hanging vertically. Okay, so if we want the spring constant, then that means we want K by itself. So we would divide by X to move this around, and our spring constant would come from force on the spring divided by change in length. Okay, we have some of that ready to go. So the change in length is here, and it's in meters like we would want it to be, but we don't currently know the force on the spring. So if we know the mass that's hanging there, and if we happen to know that's happening on Earth, or if we assume that because it doesn't mention otherwise, then we know that on Earth, 1,000 grams, which is the same as a kilogram, is going to turn into 9.8 newtons because of gravity. So sort of a combined conversion here, but it does still work. Grams will cancel grams, newtons are left over. So 119 times 9.8, divide by 1,000 from that number on the bottom, we get something like 1.1662 newtons. And I don't want to accidentally plug in the old mass, so I'm going to destroy the evidence, mark that out. And then this is now what's the weight that's hanging on the spring, which will become the force hanging on the spring. Okay, so the force on the spring, 1.1662 newtons that we just calculated, and then the change in length, 0.41 meters that we had earlier. Then the units don't really combine. Technically, they can be canceled and rearranged, and we've seen that in a potentially in a lab lesson. But newtons/meters is typically how that's left. And then from dividing these out to find a value, we get that K is 2.84439, so on, newtons per meter. So that looks like this one. Okay, now we don't always have to find the spring constant as long as we stay within the elastic limit, which basically means we don't stretch it enough to break anything. Then we're going to see that there's a linear relationship between the force and or mass hanging on the spring and the change in length. So we can set up actually a proportion with this. That linear relationship makes this really nice. If I know that 100 grams would cause a change in length of 20 centimeters, then technically I can convert this and I could find proper units similar to what I had in the last question. But if I'm not told to find the spring constant, then I don't care to find it. I can just set up, okay, well, if I know that it's 50 grams now, that's going to cause a different change in length. You can even estimate if it's double, triple, 1/4, some nice number. You probably already can see where this is going, but it's not entirely necessary to guess. We can run through and calculate. So cancel out grams. So you can see centimeters are left over. Normally, again, centimeters would be an issue, but any conversion we built into this would technically cancel in this format, and so it's not really going to matter. Okay, from here though, we need to work out and find an actual solution. So we have 100 times x, which we don't really know what to do with, so we just write down both things. But then 20 times 50 is 1,000, so that's a number we can work out for sure. Then to finish solving, divide by 100, and x is 10 centimeters. Okay, now there's an alternative format, and technically there's a few different ways, but there's another way that we're going to talk about for finding spring constant. Because the way a spring moves can be seen as a moving sort of wave, we can graph it depending on how you set it up as a circle or as a special type of sine wave. Then we can use the time of oscillation or the frequency of oscillation, depending on the information we have, to work backwards and find the spring constant. So the stronger the spring, the more force, more acceleration, faster it goes, and lower time it has. And so all of these things are connected to each other. The 4 pi squared that's here, we're going to see from sort of a special case. But what happens is the formula we're looking at, if I very slightly rewrite it, is 2 pi, because in radians, that's one full oscillation. That's going to get squared because of the old formula technically having a square root in it. Then multiplied by the mass that's on the spring, and then the period on the spring squared. Okay, so a couple of things that we have to pay attention to. The mass needs to be in kilograms so that it works out to be appropriate units for our spring constant. So 1,000 grams make 1 kilogram. Actually, don't want newtons here, and I'll show you why in a minute. But we just want kilograms. So we'll get 0.315 kilograms, which should make sense if you're sort of eyeballing this. 315 grams is less than a kilogram because a kilogram should be 1,000. So 0.315 seems to make sense for this. Now be careful. The spring oscillates 10 times in this. So we don't want 11.42. We'll divide that by 10 and find the average for one oscillation. So that's going to be for T, 1.142. Okay, so now we've got everything we need. The 2 pi part squared becomes 4 and pi squared. Pi is a special number, so it just kind of goes in, stays pi. Our mass, we converted 0.315 kilograms. And then our time, 1.142 seconds. And then from the formula, that's going to get squared. Now, if you're paying careful attention here, you might notice that the units look a little bit funny. What we're going to end up with is kilograms over seconds squared. But these all say newtons/meters. And so what happens is technically there's some information about mass that gets canceled from, or from meters that gets canceled from here. Sorry. So if we multiply those back in, m over m, then what we end up with is kilograms times meters over second squared, just sort of regrouping this a little bit, times 1 over m, which may look like I've just made the thing worse, but if you remember that this first part is the definition of a newton, then this becomes newtons over meters. So it doesn't look at all equivalent that this should turn into newtons/meters or newtons divided by meters, but it actually does work out. Just kind of a strange thing about the way the units work and the fact that the N for Newton hides some information. Okay, so if we work this through, 4 is just a number, pi squared is something like 9.86960 something. I don't know, I started making up numbers at some point, but it's just some number. So we can multiply that stuff in the calculator. What's unique to this question is a 0.315. So if you multiply that with the 4 times pi, then that's going to give us a numerator of 12.4357. Now the bottom is simple enough. 1.142 is going to be squared. Becomes 1.304164. So kind of an ugly decimal, but that's what calculators are for. Newtons divided by meters from our units we talked about a minute ago. And then final solution, dividing those gives 9.53538, so on, which with some reasonable rounding becomes my first choice. Okay, then we want to think conceptually about some of our formulas here and some of our information. Ask, excuse me, about the period of a spring. So that's a formula I mentioned earlier. So this has 2 pi in it because it tracks the oscillation or repetition or movement of the spring one time around. Then that's going to multiply by a set of physical characteristics of the system. In fact, technically the square root of those. So we have the square root of the mass on the spring divided by the spring constant. Now, if it's talking about what's happening to the spring constant is K. So remember, it's like the word constant, but it has a K instead of a C. So we're looking here. Well, 2 and pi is not going to change the answer. Think of this sort of like the factor questions that we've looked at in other places, or if you've had the lecture that you've seen there. What we're looking at, the basic structure here, If mass is held constant, these are always constant, then we're looking at the fact that this is 1 over k, and then that's under square root, even though just like the 1 over k is the main feature that's going to tell us here. If this gets bigger, so if k becomes larger, that means I'm dividing by a larger number, and so that's going to give me a smaller answer. So its position, you can also say that it's inversely related. Now technically it's the square root of that, but again, inversely related means that if this part goes up, the other part goes down. So a bigger spring constants make the period go shorter. Think about it though, that means that there's more force on the spring at all times. It's going to accelerate and change speeds more quickly. It's going to move faster. That's going to make the period get shorter. Okay, same formula, but we want to look at it from a different aspect this time. So still 2 times pi, again from radians and talking about a full movement. Then square root of the physical characteristics. We've got the mass we're trying to move, and then basically the force we're trying to use to move it. Okay, so now this question is asking us about what happens if the mass changes. Well, we bring this down, and we're looking at technically the square root of m over 1. If the constant is held constant, if these numbers are ignored, we just want to see what happens when the mass changes. This is on the top of a fraction, which means it's directly proportional. Now, technically, it's the square root of that, so it's going to grow less quickly, but the orientation and placement of this variable inside of the equation means that these are going to do the same thing. So if the mass gets longer, then the period will also become longer. Conceptually, this should also make sense, though, because if the mass is bigger, that means the item is heavier and it's harder to move. So it's going to move more slowly. It's going to take longer to bounce up and down. There's a couple of things that might help you remember. Okay, then one more question in this format. So talking about this formula for a spring, the 2 pi shows up once more. Again, dealing with radians and movement, some calculus stuff. We've got m over k. And this time it asks what happens if gravity gets weaker. Well, gravity is not in this formula. So it's not going to change anything. You could still use a spring in space. Okay, so now let's talk about exchange of energy. So we have a few questions in a row, really a handful of these that we're going to talk about for setting up our information for basically how a pendulum works. If we think about a pendulum swinging, right? So we have a pendulum, say it starts here, then it swings through some angle and it ends up here. So maybe we had this and we kicked it to the side, or maybe we drew this back and we let it go. Let's think about what we've got. In fact, probably the more common way to see this would be to start by drawing it back and then letting it swing. Okay, so if we draw this back, then we're going to input potential energy into the system, right? Potential energy because it can swing down, it can speed up, it can gain kinetic energy at the expense of that potential energy. Okay, then as it's swinging down, it's going to be gaining kinetic energy. It's going to be going faster and faster until it gets to its lowest possible point. And then it's going as fast as it's ever going to go. It's used all of its potential to speed up, and then because of the way these work, it's going to swing around on the other side and reach some maximum point over here, which technically should have been symmetrical, but there's a reason I became a scientist and not an artist. So, you know, my rough and ugly pictures will hopefully suffice. But anyway, it's gaining kinetic energy until it gets to here. Then it starts to use up that kinetic energy to turn back into potential, and then it swings back and forth. So what we want to know from this is that our total mechanical energy, so total energy is what I'll write here, is equal to kinetic energy plus potential energy. And with a pendulum, there's really only two types. This isn't like a swinging spring or something horrible like that. It's just a normal pendulum. If I want the maximum kinetic energy, so if I want my KE to be as big as possible, then that's going to happen when my potential energy is at its lowest, which is what I just described for the point here, right? It had potential when it's raised up. It's using that potential as it speeds up when it falls down. And at that point, it's going to be maximum kinetic, minimum potential, which seems to correspond with at the lowest point. Okay, then now thinking about this again, if we have a pendulum off to the side, swings down to minimum position, then swings back up again on the other side, think about what the energy is doing. So once more, remember that the total energy is equal to the kinetic energy plus potential energy. So we have potential when we first hold the ball, when we draw this back before we let it go. It uses potential to become kinetic energy. It's going really fast at the bottom. Then it slows down as it's going the other way as it's gaining that potential back. Okay, so what we've got then is maximum potential is going to be either here or here. Okay, so let's see if we can figure out why that makes sense. I'm saying that we have maximum potential whenever we have minimum kinetic energy. If these are adding to some constant total, then the smaller this goes, the more energy is turning into potential, and the more the potential is going to grow. So I want minimum kinetic energy, which happens when it's still at the beginning and still at the end of the first half of that arc. And so that's going to give me my maximum potential energy at the highest point. Okay, then turning this the other way. I think it might be obvious now, but just to drive the point, remember that our total energy is kinetic and potential combined. So similar to before, we can only share between these. We can't increase the overall total without putting additional energy or changes into the system. So if I want minimum kinetic energy, so my kinetic energy is 0 at the very beginning when I draw it back, that's whenever it has maximum potential energy. Thinking about where the potential energy comes from with the pendulum, that means that it's raised up as much as possible. So minimum kinetic energy is going to happen at the highest point. Okay, then we've already talked about this, but from the other side, total energy is kinetic energy and potential energy combined. So if I want minimum potential energy, so remember potential energy dealing with a pendulum has to do with how high it is above its minimum point. So this is going to mean at its minimum point. So it's used all of its potential. It's going as fast as it's ever going to go. That's going to mean that my kinetic energy should be at a maximum. And like we talked about, as it's swinging around, that low point is where it's moving as fast as it ever will. So that kinetic energy is maximum at the lowest point. All right, then last one of this type. Then we look at something a little bit different. Our maximum total mechanical energy. So the total energy is equal to kinetic plus potential. Well, here's the thing. We've got conservation of energy. And it's always a combination or a sum of these two things. So as long as you're not wasting energy, your total energy is just equal to your total energy. And so it's going to be maximum, minimum, or the same, depending on how you look at it, at just any point. Okay, then a few more. We're getting there. We want to talk about a pendulum and what will make things change for the period to grow or to shrink. So similar starting format to what we saw with the spring. The period, capital T, is equal to 2 pi. This indicates that it's a full oscillation for however it moves, multiplied by some physical characteristics. So in this case, we need to know the length of the pendulum and then the gravity for wherever this is at. Okay, so because 2 and pi are just constants related to radians and how the calculus for how things move in this way, if we're just looking at the length, that's not going to contribute between different questions. It's not going to make any differences. If we're assuming gravity's held constant because it's not mentioned here, we just have that the length is changing. So the format, its placement in this equation, technically it is under a square root, but it is on the top of a fraction, which means it's directly proportional. They're going to do the same thing. So if the length is longer, then the period's going to get longer. They're still going to move in the same direction. Technically, that square root's going to make the growth a little bit slower, but it is going to get longer. Length increases, period increases. Okay, this one's asking what happens if the mass changes in some way. So let's think back on our formula. We saw mass in the formula for a spring, but did we see mass in the formula for a pendulum? No, doesn't make sense. So mass doesn't factor in. So basically, just as long as the thing at the end of the pendulum is heavy enough, then it doesn't matter. If the mass is too light compared to the string or the rod that's connecting the pendulum to wherever it swings from, that's going to cause an issue. It's like you can't swing a feather on the end of a string. It's not heavy enough, but you can absolutely, soccer ball, football, baseball, bowling ball, you can hang those from a string and make a pendulum. All right, so mass just isn't here, and it doesn't matter basically as long as the object is heavy enough to really make a pendulum. Okay, then last one in this format, what happens if gravity changes? So you might remember from the one with the spring earlier, gravity didn't matter, but we had a different formula for a pendulum, and as we can see, gravity is very important. Now, it's strange to think about gravity changing, because normally we're on Earth, but you can relatively easily find YouTube videos where people are using a pendulum in space. So look that up if you're interested. But gravity potentially could change. You could have a pendulum technically on Mars and use that to measure out gravity or find some information. Okay, so from this variable, if we're changing gravity, let's assume length is held constant, 2 and pi are always constants, then what's most important here is the placement of this variable. So we want to remember that it's under a square root, or under a square root and under a fraction. There's two important pieces of information here. The inverse relationship, the fact that it's on the bottom of a fraction, is going to indicate the direction better. So if gravity gets weaker, if gravity becomes smaller, because this is on the bottom of a fraction, inverse means it's going to flip and go the other way. So that will make the period go longer. If you think about that, I think it would make sense because gravity is going to contribute to a force that's going to make that swing. If there's less force causing it to swing, then it's not going to swing as fast, right? There's less acceleration involved, and it just doesn't go as fast, which means it takes more time to go back and forth. All right, just a handful more. So we semi-recently had a gravitational force question, and this one's going to sort of mimic that. Unfortunately, my units got sent to the next line, so I'm going to bring them back up, just to make it more consistent and easy to see. So our Coulomb force equation, Fc instead of Fg, is equal to a special constant K multiplied by the first quantity of charge multiplied by the second quantity of charge, and then divided by r squared. So we saw this with gravity before, where there's a gravitational constant, and then these were masses over r squared. This one has a very similar format. Okay, now a couple of things that we want to pay attention to. This says a pair of electrons. So electrons have a certain amount of charge. Protons technically have the same amount of charge, but a different sign. So let's look at what that's going to do here. So for the electrons, that's going to mean 1.6 times 10 to the negative 19 coulombs. And because they are specifically electrons, that's technically going to be negative. Now let's see why or if or how that matters when we get a little bit further down. Then let's see, what else should we fix? Nanometers. Need to know that nano means 1/1000th of a meter. So that's 10 to the -9 power for regular meters. So I move those units, but actually I don't want to use them the way that they are. And then K is 8.99 times 10 to the 9, so very close to just 9 times 10 to the 9. Several books use that. And then the units are going to be newtons, so that's where the force is going to come from that we're looking for, but then basically works to cancel everything else. So newtons times meters squared over coulomb squared. And let's see if we can put all of this into action. So Coulomb force is still, as of yet, unknown. K is a constant that pops up in a lot of electrical and charge stuff. And, units are ugly, but that's okay. They're going to clean up in just a minute. Okay, and then for an electron, negative 1.6 times 10 to the negative 19 coulombs. And then it's a pair of these, so another negative 1.6 times 10 to the negative 19 coulombs. And then all of that goes over 2.97 times 10 to the negative 9. Remember, it was nano, so that's 1/1000th of a meter. And then don't forget that in the formula, in the equation itself, that's going to get squared. Okay, so checking through the units, I want to stress the signs here and here while I'm going through this part, but we'll see that meters squared cancel meters here that get squared. Coulomb squared cancel with coulombs and coulombs, and only newtons are left. Then looking at these signs, we have a negative times a negative, so they're going to cancel each other and make a positive. A positive force means that these things are going to create a push. They're going to push away from each other. They're going to repel. So if we have like charges, if they're both negative or if they're both positive, then we get a repulsive force or a positive force that shows that they push apart. If we have one of each, then we get a negative force. So the opposite of a push is a pull, right? So if we have one proton and one electron, or one positive charge and one negative charge, then we get a negative force, which is an attractive force, and that means that the particles or groups of charges are going to try to pull together. Okay, then thinking about how the formula is set up and how things can change, say if we wanted a bigger answer here, we can make bigger charges, right? Because they're on the top of the equation, so bigger charges would make a bigger force. If we wanted a smaller force, then we could use smaller charges. Be careful, because if we think about radius and how that would change, radius is on the bottom of this equation. So if there's a bigger separation, there's actually going to be less of a push or pull, and by a greater degree because there's an exponent. So like if they're twice as far apart, then there's only 25% of the force, 1/4 of the force, because it's on the bottom of the fraction and they get squared. All right, but enough distractions. Let's see if we can find the actual answer to this question. The bottom part is potentially easier to work out. If we take 2.97 and square it, evidently we get 8.8209. And then dealing with the exponent, we had 10 to the negative 9 that got squared, so it turns into 10 to the negative 18. Then newtons were the only force or only units left over, and they are for force, so it makes sense for what we're trying to do here. So we have newtons. Then multiplying the top together, multiplying all of these things will give us 2.30144, and then times 10 to the negative 28. Okay, then if we divide these, we're still going to have newtons. Scientific notation, if you peek at it and glance or estimate ahead of time, almost looks like it's going to be 10 to the negative 10 because of this difference. But because 2 is smaller than 8, it ends up bumping the decimal an extra time. So we actually end up with 10 to the negative 11 here. And then after that, dividing these two and working it out, simplifying if necessary, 2.609. I ran out of room, but it's followed by another 0, so that's pretty close. It looks the most like this one. Okay. Then going a little bit more simple here. We want to find the resistance necessary to create a certain amount of current given a certain potential. So a couple of things to talk about here. You can make potential several different ways. So you can have a 9-volt battery. Those are little rectangular batteries. It's probably not good to do this. We used to stick them on our tongue and it would tingle because it would, I guess, flow through your tongue. So probably don't do that. I don't know if it's really great for you, but that was something we used to do a bunch. Though we could also make 9 volts by using a bunch of, say, AA or AAA or C or D batteries. So keep in mind that the potential doesn't have really anything to do with the size of the battery. But we could take, say, 6 times 1.5 volts. So most disposable batteries like AA, AAA, C, and D, most of those are in the 1.5 volt range. And you need to make sure that you understand that if you were to do this, if you could put those in series, then you could effectively make the same thing. So in a series orientation, what that's going to mean is, say you set up the batteries and you pay attention, you put positive, negative, positive, negative, positive, negative, like that, then they're going to add up and give more and more and more potential. So I guess I could draw the rest of the picture. I'm almost there. Positive, negative, positive, negative. Right? That's 6 pairs. So here's a battery, 3, 4, 5, 6. Yeah. So if these were all, say AA batteries in series, then that would make 9 volts total. Now you have to be careful because if you were to accidentally make them go in backwards, so say I had one battery, it was positive, negative this way, but then the next one went in negative, positive, and then say I did it again, so positive, negative with this one, but this one's negative, positive, and say I do one more time, positive, negative, and then I make this one go negative, positive. Well, this battery and this battery are going to cancel each other out, and this battery and this battery can cancel each other out, and this battery and this battery cancel each other out. So if you've ever accidentally put a battery in the wrong way, and the whatever device you were using, a remote or something, game, whatever, didn't work, this is why. Those potentials were working against each other. So it's important that if you're putting in batteries that you arrange them correctly. Okay, well, with that small detour though, this question is actually pretty quick to work out, believe it or not. Just talked like 5 minutes about batteries. But as far as what we need for just this question, Ohm's law says that the potential across a battery is equal to the current that will run through the circuit multiplied by the resistance of the circuit. This could be something simple like just hooking up a light bulb or an LED, but in general, this is our formula. Okay, if I want to look for resistance, I want to solve for R directly. Then a little bit of algebra would move the current out of the way, and our resistance is going to come from the potential divided by the current. Okay, well, we have those pieces of information. Somehow or another, we've made 9 volts. Our current here is 0.0455 amps. So a lot of times we see milliamps instead, just because currents can be very, very small. This would be 45.5 milliamps, but this was converted to be convenient here for solving. Okay, then numerically, this is going to give 197.802. And what's weird about this is you would think, okay, well, it's volts divided by amps. Well, I know it's, combinations of, like people's names and things from a long time ago, but as if by magic, a volt divided by amp, as it turns out, is an ohm, which makes yet somebody else's name from a long time ago. Okay, but if we take this and we round to the nearest answer, then looks like 198. Okay, then we're getting there. Just a couple more. So let's think about this. We've got a circuit created by a trio of 10 ohm light bulbs in series. So what we need to know, there's a couple of different ways to look at this. Excuse me, but the total potential, if it's in series, so if we have 9 volts in series, is going to split and be used across the different resistors, which in this case are the different light bulbs. Because they're all the same size light bulb, then they're each going to use up a certain amount of this potential. So the first light bulb is going to use up 3 volts. The second light bulb is going to use up 3 volts. And the last light bulb is going to use up 3 volts to make the full potential of the circuit. So each each light bulb only sees 3 volts. Okay, let's think about what this means and compared to 10 ohms in parallel. So units got suspended on the next line, but that's okay. So in parallel, if we have 9 volts, then that's going to turn into 9 volts and 9 volts and 9 volts. And so it's kind of weird, but that same potential splits and goes along all the different paths, possible multiple paths around the circuit. Basically, it's like running several circuits next to each other, which is where the name parallel comes from. So if we think about this here, each light bulb is going to see 9 volts here. So it's going to see more potential. It's going to try to push more current across that light bulb. And so pushing more current across that light bulb means that it's going to be brighter. So, oops, I missed on my circling. So the bulbs in parallel are going to be the brighter ones. Okay, so let's see if we can put together some information and maybe get a little bit of a better understanding on that one. So here we're talking about total current. We've got potential. We've got a resistance. So we're definitely looking at an Ohm's law sort of question. It says that the total current is what we're looking for. So we're looking for I, which means we can divide R and we can move it over. So I is equal to V over R. Okay, so this is a pair of bulbs. So, it's a little bit easier, I think, to deal with these 2 at a time instead of 3 at a time. So, our follow-up examples are, since we're running the actual numbers and finding the math, are made to be a little bit simpler. Okay, and there's a couple of different ways that you can do this. The one way that we can do this, we can say that we've got 9 volts of total potential. And then if we look at the current that's going to run through the full circuit, then that's going to come from 2 times our resistances, because they're the same as each other. We can just double it up. We can also think about it this way. This is kind of a special case, again, because it is a pair. That's going to be important here. But remember that I said that if we have identical resistances, like identical light bulbs, that the potential gets shared between those. So I have 9 volts divided by 2, and then that's going to divide by my 10 ohms if I'm looking at one light bulb. So in series, every light bulb, every part sees the same current. That's why this formula works out in 2 different ways. If you know some algebra tricks, then you'll even kind of see how this 2 could be rearranged and moved to the bottom, and it's the same thing. So if I'm going to work this out now, I'm either going to have 9 volts divided by 20 ohms, or I'm going to have 4.5 volts divided by 10 ohms. And in either direction, this one might be easier to see, but you're going to have 0.45 amps. Weird arrangement of the units, but a volt divided by an ohm does make an amp. And we're looking at this one. Okay, basically the same question again, but this time we have a pair of light bulbs and they are in parallel. So thinking about Ohm's law again, V equals IR. If we're looking for the current, we saw this before, but we can slightly rearrange so that current is equal to potential divided by resistance. And then there's a couple of different ways that we can see this. Our current can come from the 9 volts of potential. Now, in parallel, these are really strange, and it sounds odd, but in parallel, your resistance actually goes lower, having more objects. Thinking about it this way, when you have more objects, more loops of current for how the electricity can flow, it makes it easier overall for more electricity to flow. It's like multiple routes or avenues. So what's going to happen here is we've got the same 9 volts, but we're going to see actually half of the resistance. So 10 ohms gets divided by 2 when it's in parallel. because there's an equal pair of these. So it looks strange, but mathematically it actually is correct. Or if we're trying to find the total current running through the setup, then we can keep in mind that technically there's 9 volts running through each loop. So we could say the 9 volts happens twice. We're thinking about basically each light bulb and then combining them. Each of those is a 10 ohm light bulb. And if we simplify here, for this first one, we're going to have 9 volts over 5 ohms. Or this other one, we're going to have 18 volts over 10 ohms. And either one of these is going to divide out to give you the same answer. So I do, it might be easier to see with this one because that's just a 10. It's like moving the decimal. But I end up getting 1.8. I guess to match the decimal places from the answer choices, though, I'll say 1.80. Volt divided by an ohm once more is an amp. There we go. To really drive in the point, though, that parallel circuits are basically independent circuits from each other, tied in and running next to each other, we can calculate directly one light bulb at a time and see what the answer is going to be. So determine the current through one of the light bulbs. So we're thinking Ohm's law again, V equals I times R. We've got 9 volts here and 10 volt resistance, so good setup. We're looking for current, which is a formula we've already seen. So that's potential divided by resistance. And each loop is going to see the same 9 volts over and over again. But if we're looking at one light bulb on one loop, then we're just looking at the 9 volts once. Okay, and then if we're looking at one light bulb, then we're looking at one of those resistances. And so basically this is the same as just having a single light bulb just on its own in a circuit. So I have 9 volts divided by 10 ohms. Then that's going to give me 0.9 or 0.90 if we match the decimal places here. A volt divided by an ohm is an amp. So that looks like this one. Okay, as far as this group of material, that should be most of what we need.